The limbic system mediates and controls all aspects of emotion and motivational functioning, including sexual behavior, the desire for food, feelings of anger, rage, and even the most sublime of emotions ranging from love to religious ecstasy. Typically, the limbic system has been associated with what some scientists call the 4 F's: feeding, fighting, fleeing, and sexual behavior. The principal structures of the limbic system include the amygdala, the hippocampus, the septal nuclei, the cingulate gyrus, and the hypothalamus. For the purposes of this lecture, we will concentrate on the amygdala, the hippocampus, and the hypothalamus. Okay, buried in the depths of the temporal lobe are these two structures that we want to focus on: the amygdala and the hippocampus. And we learned earlier today about the amygdala involved in the fear response. In fact, stimulation of the amygdala, there's actually different nuclei, lateral and medial, which we'll get into next lecture. Abnormal activity in the anterior temporal lobe, or you go in and stimulate the amygdala with an electrode. One of the most common reactions is fear, incredible fear reaction from stimulating the amygdala. Yet other reactions you can get is not just fear, you might get rage. Another reaction you might get is increased sexual feelings. The amygdala is like the prime senior executive of the emotional brain. It's that part of the brain that enables you to feel love, to feel affection, to feel happiness. The amygdala controls all aspects of emotion, including social, emotional behavior. Some people suspect that there's damage in the amygdala in people who have autism that didn't develop properly. So the ability to recognize a face as a happy face or a sad face, there's facial neurons in the amygdala as well as in the temporal lobe. The amygdala is constantly surveying the environment for individuals, objects, items that are of motivational significance. There are auditory fibers. It receives auditory information, receives visual information, it receives tactile information. In consequence, if you were hungry and you were looking at something good to eat, it's the amygdala which enables you to identify something that might be good to eat. The amygdala will in fact fire when you're looking at something that's good to eat. So the amygdala assigns emotional significance to everything you see, hear, and feel. And if we took out the amygdala, you would lose the ability to recognize emotion, you would lose the ability to socialize, you would lose the ability to recognize a male versus female, your sexual behavior would be completely abnormal and abolished. You hear a sound, you hear a voice, your ability to determine if it's happy, sad, etc., made possible by the amygdala. You're looking at somebody who's frowning at you or angry at you is made possible by the amygdala, because it's getting all this visual information, and it's also getting all this auditory information, and it's also directly connected to the temporal lobe. It also has connections with the parietal lobe, so that emotion regarding the body can also be perceived. In any case, the amygdala is this major, fantastic, important structure, and you have a right amygdala, you have a left amygdala, and the amygdala is actually divided up into different nuclei, which I will discuss. The amygdala also is sexually differentiated. So in consequence, also, the amygdala sexual behavior. Stimulated in a male, he might get an erection. Continue to stimulate it, he might ejaculate. Stimulated in a female, she might take the lordosis posture, doggy position, and she might also have orgasm by continuing to stimulate. There's also facial recognition neurons that can recognize male versus female. So this is a convenient little structure here, because if you have a male brain, for example, and you're able to distinguish male versus female. You're able to distinguish if the female is smiling or if the male is angry, all again made possible by this one particular structure, amygdala. And in fact, the rope of fibers connecting the right and left amygdala, the one in the right hemisphere, one in the left, is also sexually differentiated. It's in fact, I think, 18% larger in females. And in homosexuals, it's like 35% larger. Which might explain the question came up earlier about females being more emotional. Well, if the two amygdala have a greater opportunity to interact, we might see why females might be more emotional, because the two main structures involved in emotion. There's all kinds of studies showing females are superior at discerning emotion. at discerning social emotional nuances. So they go in a situation with a guy who's unaware of all these complex little social emotional events taking place, but females all analyzing all this information. What this means is females have a social emotional superiority. That is, females are able to perceive all these complex social emotional nuances as conveyed through body language, as conveyed through the face, as conveyed vocally through speech patterns, whereas males have a much more limited ability to perceive as well as express social emotional nuances. So whereas females might go home and complain that their husbands or boyfriends aren't sharing their feelings, well, the reason is males have less feelings. That's a joke, but what I really mean by this is that females, when it comes to social emotional expression and perception, as numerous studies have shown that females are social emotional geniuses as compared to the male. Okay, I want to stress, there's a male amygdala, there's a female amygdala, and there's a homosexual amygdala. What I mean by that is that the amygdala is sexually differentiated such that there's a male pattern, there's a female pattern, and there is a homosexual pattern. Because the amygdala can tell the difference between male and female faces, can tell the difference between a smile versus a frown, the male limbic system is therefore able to recognize a female versus a male face. Likewise, because the amygdala also has neurons that respond to, they can determine if a person's looking at them versus looking away, a male amygdala might respond to somebody staring at them with comments such as, "What are you looking at?" Versus if it's a female that looks and then looks away, the male will not respond with aggression but may instead realize that the female is flirting. Likewise, because the male amygdala is sexually differentiated and controls all aspects of social, emotional, and sexual functioning, including sexual arousal, this means that a male with a male amygdala would look at a female and might experience sexual arousal, whereas a female would be looking at a male and experiencing sexual arousal. By contrast, the homosexual, because they in fact have a amygdala that's organized in almost a hyper female fashion, they too would be able to tell the difference between male and female, but they would look at males and they would feel sexual arousal. In other words, just as a person with a male amygdala would look at a female face and female body and might feel sexual arousal, and just as a female might look at a male face and a male body and respond with sexual arousal, a homosexual with essentially a female amygdala would be looking at male bodies and also be experiencing sexual arousal. Primary structure involved in all aspects of felt emotion. All the complex emotions are made possible by that amygdala. The ability to feel sexual desire, the ability to have certain preferences in food, soft drinks, sex partners, the ability to feel love and affection, all complex emotions, including even religious ecstasy, made possible by the amygdala. It's the seat of social and emotional intelligence. It's the main structure involved in all aspects of higher complex emotions. The amygdala is directly linked, the medial, the older, more ancient part of the amygdala, is directly linked to the caudate putamen, which is also known as the striatum, which is located in the central part of the frontal lobe, which has massive interconnections with the motor area and also with the cerebellum and brainstem. Huntington's chorea, Parkinson's disease, motor abnormalities, we see disturbances in these structures. The medial part, the more ancient part of the amygdala, is directly linked to these motor centers. The lateral is more linked to the neocortex, and that's why in sharks and what have you, they don't have a lateral, whereas we do. The lateral and the medial amygdala, we'll just consider it together. You go into the amygdala, as I said before, you stimulate it, a certain area, and the person or animal will first feel anxiety. You continue the stimulation, they might feel fear. If they feel fear, they might run away. How might they run away? Because it's acting on the striatum, which is involved in motor activity. Stimulate these areas of the brain. You might get kicking, you might get punching movements with stimulation of this area. So the amygdala is interacting with the striatum, and the striatum will be topic of another lecture. The amygdala is also involved in emotional memory. It's the main emotional memory. So if you had terrible experiences when you were a child, it's the amygdala that stores that information. If you fall in love and then you break up and you walk out and every time you see a red car, it reminds me of her red car. That song reminds me of her. Emotional memory is being made possible by that amygdala. And what the amygdala is doing is actually storing, it processes the emotions and then it actually will store it in different parts of the brain. And the amygdala also enables you to retrieve those emotional memories, where it's the frontal lobe that will help you stop thinking about those emotional events. So amygdala is involved in emotional memory. By contrast, the hippocampus, the anterior hippocampus, is also involved in memory. The left hippocampus would be listening to me talking, would be storing those words and phrases and sentences, and in consequence, if the temporal lobe was damaged, and the left temporal lobe in particular was damaged, and this structure was destroyed or removed, from that moment on, you would not remember anything you said. You would not remember anything you read. Your whole auditory verbal life stops at the point of that destruction. You will never store another verbal narrative reading memory again. There have been people, including patients I've seen, who have had both temporal lobes destroyed. They have no memory from that point on. There's a famous case of HM, a guy named Henry, who had both of them surgically removed. Brendan Milner, famous neurosurgeon, worked with him for 20 years, saw him every day. Every time he had no memory of meeting her. His whole life stopped at the moment of losing those structures.
Why did he have them surgically removed?
He had temporal lobe epilepsy, and to try to control that, there was damage in here, so they removed and discovered that from that moment on, he couldn't remember anything. According to him, he says, every day is brand new to me. Everything's brand new. The limbic system constantly surveys the environment for items and objects and people and animals that are of motivational significance. The amygdala and the hippocampus store this information in memory. In fact, these two structures interact with one another so that complex memories and their motivational significance can be stored in memory. The amygdala and hippocampus, however, are also influenced by other limbic system structures, in particular the hypothalamus. In fact, the hypothalamus in turn greatly influences the amygdala, and the amygdala greatly influences the hypothalamus. There is a complex interactional relationship between these structures. Many years ago, a neurosurgeon by the name of Heath made an amazing discovery when he began inserting electrodes into a patient's brain. And lo and behold, that patient reported feeling extreme pleasure. Heath is putting these electrodes in his neurosurgery patients. These are people he's going to scoop out part of the brain, take out tumors, and he's stimulating and asks people to describe their experiences. When all at once he gets to this one area of the brain, and the patient goes, whoa, that feels good. And he turns up the stimulation, and the patient, that feels really good. And moved it around in different areas, and lo and behold, discovered there are areas of the brain that when you electrically stimulate it, the person will feel extreme pleasure. And what Heath, this neurosurgeon, discovered was that the brain indeed can experience different sensations, including the ability to experience pleasure. Now, first, this was dismissed. Oh no, that's impossible. Ignorance is almost like an addiction, and some people find it very hard to give it up. But in any case, so Heath was ridiculed, these couldn't really be real, and then another neuroscientist by the name of James Old, he took little rats, and he implanted electrodes in different areas of the brain, different areas of the limbic system. Rats are really smart creatures, incredibly intelligent little animals, which is why they're a favorite of using for experiments, because you can teach them very easily to perform complex acts. And one of the most simple acts a rat, you will train them, is to bar press for a reward. So a rat will press, and here comes a little food pellet. So they can quickly learn to do complex, including mazes, run all over to get to the bar press and press it. Here comes the food pellet. You can think of people in Las Vegas pulling on those bars. It's basically the same thing. Get your little reward, the little coin comes out. But, so what Olds did, he implants electrodes in different parts of the rat brain. And what he discovered was that when he planted electrodes in an area called the medial forebrain bundle, MFB, medial forebrain bundle, that lo and behold, these rats would go up to that bar and they would start pressing the bar to get electrical stimulation to that part of the brain. So rats would actually go to the bar press mechanism simply to be stimulating that medial forebrain bundle. So here's the electrode coming out, the little lever, rats pressing the little shock, and so they go, oh, that feels good, and whatever rat language, they're basically feeling what people would deduce is extreme pleasure. Well, this was quite revolutionary, and Olds would have got the Nobel Prize if he didn't drown a couple years later. He starts putting the electrode in different parts of the rat brain, and lo and behold discovered there were a variety of areas that would also support self-stimulation. There's pleasure centers all over the brain, all these little variety of areas. But what Olds discovered is that when he put an electrode in the lateral hypothalamus, that he got an incredible amount of self-stimulating behavior. Once he got into the lateral hypothalamus, rats would bar press, they would ignore food, they'd ignore water, they would ignore willing sex partners, they would continue to press to the point where they felt complete fatigue and would finally fall over in need of sleep. So discovered that the lateral hypothalamus was this one area where the most incredible amount of self-stimulatory behavior would occur, and it turns out the hypothalamus, therefore, all these different experiments have been done, that the lateral hypothalamus is the pleasure center. The pleasure center, the area that supports all your ability to experience any kind of pleasure whatsoever is made possible by this lateral hypothalamus. Now there's all kinds of different hypothalamic structures and nuclei, but we're just going to concentrate on three today, and one is the lateral and one is the ventral medial. In any case, again, so these rats are mark pressing, press, to get that primary electric shock into the lateral hypothalamus, and he puts the electrode in different areas, and he discovered that when the electrode was placed in the ventral medial, that rats would actually bar press to turn the stimulation off. So he would put an electrode in the ventral medial, constant little current, giving little shocks, and rats would learn to start pressing that thing to turn the stimulation off. So basically what he discovered and what other scientists discovered is that the lateral is a pleasure center, whereas the ventral medial was like a unpleasure center, an aversion center, would actually decrease any pleasurable feeling and induce negative feelings instead. What we have here basically is similar to what Freud described as the id that says I want it now, and the id being the most primitive aspect of the unconscious, and the id being the source of the pleasure principle. And according to Freud's theory, we're all governed by the desire to have pleasure and the desire to reduce tension. So there's these two opposing mechanisms at the basic level of our unconscious which motivates all behavior. One is to increase pleasure, and the other is to decrease tension, decrease any sensations of unpleasure. And lo and behold, we find these structures in the hypothalamus which actually mediate that. So in some ways we could call the hypothalamus the id in the Freudian sense. That the lateral hypothalamus is involved in eating and drinking food. The hypothalamus contains a variety of receptors, including lipostatic receptors, osmoreceptors, glucose receptors, all these little receptors in the hypothalamus which are sampling blood flow to determine what your nutrition, if you need water, if you need food, what your fat level is in the body. If there's need for nutrition, the lateral hypothalamus will become active. fact, the lateral hypothalamus becomes active if you're hungry, it becomes active if you're looking at food, and it becomes even more active when you're eating. And that makes a lot of sense because eating is a very pleasurable activity. So here we have the lateral hypothalamus is like an appetite center, which is inducing people to eat when they're hungry and feel pleasure when they're eating. Also, the same thing with water intake. They find that they go in and stimulate the lateral hypothalamus and animals would start eating even if they're not hungry, drinking even if they're not thirsty. Conversely, the ventral medial, you stimulate the ventral medial and animals stop eating, they stop drinking. So we have this like unique little, like a thermostat. The temperature at 90, and maybe at 75, temperature goes up to 90, okay, and feedback mechanism turns off the thermostat. The hypothalamus working the same way with these nuclei. So we have these two, the ventral medial and the lateral. So you get hungry, the lateral is going off, you start eating more food, you get to a certain point, you feel full, you no longer want to eat. And what's happened is now the ventral medial is becoming active and the lateral is reducing activity. So it's this nice little mechanism. There's also other factors like distension of the stomach. But here's these neat little structures working back and forth. You're hungry, the lateral's going off. You start eating, getting a lot of pleasure. You eat more and more and more, then the ventral starts becoming active, the lateral becomes less active, and you stop eating. What other scientists discovered, you go into the ventral medial and you destroy the ventral medial, the animal will start eating and eating and eating and eating and drinking until the point of incredible obesity. By contrast, you destroy the lateral hypothalamus and the animal stops eating, stops drinking. In fact, they'll just simply waste away unless force-fed. We can think in terms of human beings, for example, anorexia. Mentioned before a possibility about abnormality perhaps in the parietal lobe, making ladies think they're fat when they were skinny. It's also possible there could be abnormalities in the hypothalamus that could be contributing to anorexia, so that ladies feel full when they've eaten a piece of lettuce and start feeling very uncomfortable if they eat 2 pieces of lettuce. One hypothesis is that in cases of eating disorders that there might be abnormalities in the hypothalamus. You stimulate the hypothalamus, a certain area, and the person can fly into a rage, extreme rage, baring their teeth, trying to attack. If nobody's there, they will attack nothing at all. Done the same thing with animals. Stimulate in the hypothalamus, the animal would go into an extreme rage and try to attack, bite, scratch. If a person's there, they would go for them. If nobody's there, they would just simply be attacking thin air. However, what they discovered is that if you turn the stimulus off, the moment you turn it off, the animal's in a rage, the human's in a rage, turn the stimulus off, the rage goes away, just like that. Some scientists call it sham rage. Say, well, it's not real rage because there's no mood. There's no mood associated. You can just simply turn it off because we know if we get really mad, we're mad at the teacher, he gave us an F, I'm mad at that guy, I'm going to go tell the dean. You stay mad for some time. It's not good. On and off, on and off. The reason it's on and off is there's other structures in the limbic system which can drive the hypothalamus, such as the amygdala. We see these massive connections. Humans that have had that stimulation and fly into the rage and turn it off, they say, well, I didn't feel mad, but they were acting in a rage. Now, another emotion associated with the hypothalamus is laughter. This was also first discovered around the 1950s. A neurosurgeon, he's removing a tumor in the hypophysis, but every time he touched what was called the infundibular region, located right about here, the patient started laughing. Ha 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 ha! Ha 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 ha! Started stimulating more, and the person not only started laughing, but you can get, that doctor, person was engaged in hilarious speech. But you turn it off, and again, the laughter would go away. So, call that sham laughter. And the person would say, well, when it was being stimulated, I didn't really feel happy, but I was laughing. This young man goes to the funeral of his mother, and she's being lowered into the ground, and he's standing there, and he's crying along with other people, and all at once he starts, ha 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 ha. He started laughing, and laughing, and laughing, and you've heard of this. Sometimes you laugh until you cry, and some people cry until you start laughing, but So we could make up all these psychological mechanisms of why he might start laughing while his mother's being lowered into the ground. Maybe she was abusive, a bad mother, so he's happy to see she's being put away finally into the ground and covered up. But he started laughing and laughing and fell to the ground. He continued laughing, and ambulance called, and then the laughter stopped. And he was very embarrassed, had no idea we started this laughing, got home and started laughing again, like laughing and laughing and laughing. They didn't have 911 then, but they called the ambulance, comes and picks him up. He's laughing to the point where he couldn't hardly breathe, and he ended up dying laughing, because he was laughing, ha, 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 to the point where he couldn't get a breath in. So laughter is not, laughter is ha, 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 the air coming out of the lungs and the mouth. So this guy's going ha, 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 and he became cyanotic and died. And when they did the autopsy, lo and behold, they discovered tumor growing in this region. So it had no psychological things that we could blame on his mother. It was actually a tumor growing in this particular region, causing the person to engage in sham laughter. And there's been a number of cases like this of people laughing to death, and then discovering later there'd be a hemorrhage, so blood flow in here pressing on this area. So the hypothalamus mediates all these complex emotions such as rage, laughter, pleasure, unpleasure, eating, drinking. It is now well established that the hypothalamus, and in fact many regions of the brain, are sexually differentiated. What this means is that there's a male, female, even homosexual limbic system, and that these particular structures have a female neuronal pattern or a male pattern or a homosexual pattern. We know that structures such as the hypothalamus are particularly sensitive to circulating steroids during the early stages of development. And in the absence or presence of testosterone, you would develop either the male or female pattern of neurodevelopment. In particular, we know that the preoptic area of the hypothalamus and the ventral medial and the anterior nuclei of the hypothalamus are all sexually differentiated. Also, we know that the suprachiasmatic nuclei are also sexually differentiated. The preoptic region in particular is important in that not only is there a male versus female pattern, but the female pattern is necessary because the female brain has to mediate incredibly complex functions which need not be performed in the male brain. For example, females get pregnant. Females have a menstrual cycle. The preoptic area is involved in the secretion of oxytocin, gonadotropins, follicle-stimulating hormones, luteinizing hormones, estrogen, progesterone. All these hormonal changes are important during the cyclic changes during female's menstrual cycle, including when she becomes pregnant and lactating. For example, during lactation, not only is there an increase in luteinizing hormone, but oxytocin. And oxytocin and these hormones are involved in lactation, including even the ability to feel pleasure while the female is nursing. In addition, we know that stimulation of structures such as the preoptic nuclei, in males, for example, if you stimulate the preoptic nuclei, males will begin sexual posturing, they'll get erections, they'll make copulatory movements, there'll be pelvic thrusting, there can even be an explosive discharge of semen. Likewise, in females, you stimulate these particular nuclei and the female will begin posturing. Conversely, if you were to lesion the preoptic nuclei, you get a total loss of sexual interest and there'd be gonadal atrophy. The testes would simply shrink up. In addition to the preoptic, ventral medial, and suprachiasmatic nuclei, the anterior hypothalamic nuclei is also sexually differentiated. And we know, for example, that the ventral medial structure in the hypothalamus, that not only is there a male and a female pattern, but there's also a homosexual pattern. And that what this means is that the neuronal pathways and structures and dendritic and axonal interconnections within these structures differ between males, females, and even homosexuals. So these particular structures are not only sexually differentiated, but they're involved in sexual activity. When you stimulate with an electrode, you get male versus female sexual activity. And in fact, these structures are involved in all the hormonal changes associated with the menstrual cycle and pregnancy. Thus, the very core of our being is male or female or homosexual. And this may well account for not only sex differences in emotion and behavior, but also sex differences in thinking. As an aside,
Again, consider anorexia and the role of the ventral medial nuclei in controlling appetite and hunger. We find that these structures are sexually differentiated, and this raises the possibility that anorexia in females might in part be due to disturbance in the ventral medial part of the brain, which is sexually differentiated. Lastly, let me stress, it again is the presence or absence of testosterone which induces or triggers the male versus female pattern. In the presence of testosterone, you obtain the male pattern of sexual differentiation not only in the hypothalamus but in other structures such as the amygdala. In the absence of testosterone, the female pattern develops.
Here's the olfactory bulb. The limbic system, in part, evolved out of the olfactory system. In fact, it's called, this part of the brain is called the rhinencephalon, nose brain. So, in related to your question, which most apropos or statement is, yeah, maybe they could sniff them out because the amygdala and all these structures are involved in perceiving odors, including pheromones. Mentioned before, amygdala, hypothalamus, sexually differentiated, male and female patterns. Amygdala, incredibly complex structure receiving tactual, visual, auditory, as well as olfactory stimuli. Spoke before about ovulation, pregnancy, why it's necessary for female to have a female brain to perform these kind of operations. Complex, female brains even more complex than the male. Common experience, females living in dorms, is that they all or most will begin menstruating at the same time. Very common experience. Why is that? How could they all begin menstruating at the same time? And that's because humans, like all other animals, are secreting pheromones, including sex pheromones. If you have a female dog and she has it fixed and she goes in the heat, suddenly you're being visited by dogs, male dogs miles away. How do they know? Well, they're picking up on the olfactory chemicals, the pheromones. In fact, most animals, sexual intent is communicated through pheromones. Humans, we spend all this time trying to get rid of every single body odor. But so one hypothesis is that females, when they're going through their cycle, is that they're releasing these chemicals, which are actually signaling what their state is, and that other females pick up these pheromones and they become synchronized, so they all begin menstruating at the same time. So here again is more evidence of sex differences.
The suprachiasmatic nucleus is also sexually differentiated, and the suprachiasmatic nucleus is directly linked to depression. That is, disturbances in the suprachiasmatic nucleus, also referred to as the SCN, has been linked to a condition called SADS, seasonal affective disorder. And we know that disturbances within the SCN also results in low levels of serotonin. That is, the SCN directly mediates and influences serotonin levels, whereas low levels of serotonin in turn are associated with profound depression. This could well explain why females are more prone to mood disorders and why females are also more prone to developing postpartum depression. That is, as this structure is involved in all aspects of sexual behavior, including mediating hormonal changes related to pregnancy, related to lactation, that therefore disturbances in this nucleus might give rise to postpartum depression in females and also account for the greater incidence of depression, which is more severe and occurs more frequently among females than in males.
Let's say you're a little kid, you're at home, mom and dad are yelling, screaming, and hitting and smashing things. Even if they're not bothering you, you're going to feel, little kid's going to feel incredible amount of stress. Or let's say that you're in Iraq fighting for freedom and democracy, and you're watching your fellow soldiers getting blown up, people losing their arms and legs, people shooting at you. You go out every day, you're worried about what's going to happen to you. You're going to be under a lot of stress. And commonly, typically what happens when you feel a lot of stress, a variety of chemical reactions occur. Certain neurotransmitters are released in greater amounts, one of which is norepinephrine. Initials would be NE. Many of you may have heard the term adrenaline. Well, in scientific terms, we call adrenaline, we call it epinephrine. Noradrenaline is called norepinephrine. They're basically the same name, but just to make it difficult for all of you, they came up with norepinephrine and epinephrine. And maybe some of you heard, get your adrenaline going. Okay, you really don't get your adrenaline going. You get your noradrenaline, your norepinephrine going when you're aroused, you're sexually aroused, you're involved in fighting, you're under amount of stress, you're emotionally aroused. Massive amounts of norepinephrine begin being secreted. Norepinephrine would help the body, for example, fighting or fleeing. It's arousing, activating. So norepinephrine involved in arousing and activating the body and the brain. A lot of norepinephrine going into the amygdala, amygdala being that major nuclei in all complex emotions, including the fear response, including running away or fighting and fleeing. So all this amount of norepinephrine going up into different areas of the brain to activate the brain. Because if you're under stress, it's typically in a situation where you want to fight or flee or get away. You don't normally just lay back and let the stress happen to you until a certain point. Norepinephrine also serves a protective function. And what I mean by that, to give it an analogy, consider you're racing your Volkswagen down the street at high speeds, engines roaring away, and what prevents the different parts from damaging is that nice oil in between. Okay, if you run out of oil, the metal starts rubbing together and you destroy your engine. Norepinephrine, not like oil, but it also serves a protective function. Let's consider if you're aroused, the brain is highly active, the amygdala is highly active, and if it's highly active, it can become to the point where it gets damaged from all the incredible amount of activity. So norepinephrine is serving a protective function as well as arousing the body and the brain. So it comes in here between, protects synapses, for example. At the same time, you're under tremendous amount of stress. The hypothalamus is secreting all these different neurochemicals, one of which is called ACTH. And there's a variety of synthesis and neurochemical reactions occurring, which results in the secretion of cortisol. Cortisol. You're under stress, you're a little kid, mommy and dad are yelling and screaming, you're in Iraq watching your friends getting blown apart, norepinephrine keeps going up because you're under stress, but at the same time, cortisol is being released in massive amounts. Norepinephrine also serves to protect the brain against cortisol because cortisol can damage the brain if it's in high amounts. Here's what happens. You're under a lot of stress. You see a car accident, you're under stress, norepinephrine level goes up, cortisol levels, somebody's yelling at you, you have these temporary episodes of stress. But let's say you're in a situation where you're in battle, frontline combat, you're constantly being stressed. Every day you're being stressed, week after week, month after month, and you're seeing a lot of horrible things happening. So you're constantly under stress. You're stressed every single day. Or let's say again you're that little kid and mommy and dad are yelling and screaming and hitting and smashing things, and they could go in and be real loving to you, but you're going to be under stress. Let's say it's even worse. Let's say it's the guy next door, it's a stepfather, and he's coming in to have sex with you. And you're a boy or a girl, and he's coming in there to have sex with you, and he's being mean to you, and he's threatening you, and he's hitting you, and he might be doing bad things to you. And every night, you're laying there under stress, worried, he's going to come in here and do these things to me. So you're constantly under this tremendous amount of stress. What can happen, it's just like a muscle. If you use it and use it, the muscle gets bigger. You keep activating a certain area of the brain, you're going to have neurons, dendrites, axons. Neuron gets bigger, axons will grow. The brain can become adapted to being under constant stress. And if it becomes adapted to be under constant stress, it's always going to be ready to secrete cortisol and for norepinephrine levels to go up at any time. And they're going to affect structures like the amygdala. So even after the stress is gone, you might still feel fear, you might still feel upset, something you hear might remind you of it, you might startle easy. I'm talking about if you're under chronic stress. Something that might develop is what we call post-traumatic stress disorder, PTSD. What happens if you're under chronic stress, the hypothalamus, hypophysis, these structures will become adapted to secreting massive amounts of cortisol at any time. But here's what also happens if you're under chronic stress, repetitive stress. It goes on hour after hour, day after day. What happens is cortisol secretion continues, but norepinephrine levels start decreasing. Synthesis goes down. Norepinephrine levels start dropping. And that sets the stage for PTSD and all kinds of horrible things, because when norepinephrine levels go down, you have all this massive amount of cortisol, and the cortisol will actually start damaging the brain. It'll start damaging structures such as the amygdala and the hippocampus. Neurons will start being destroyed. Synapses will start being destroyed. Dendrites will start being destroyed by all this massive amount of cortisol being secreted. So what we have here, persons under chronic stress, cortisol is being released, norepinephrine is being released, norepinephrine levels start going down, cortisol starts activating on structures such as the amygdala and hippocampus and other brain regions. Before it starts destroying this area, these areas will start developing paroxysmal abnormal activity. So we get abnormal activity in the hippocampus, we get abnormal activity in the amygdala, where the person is under this tremendous stress, when norepinephrine levels have gone down, the cortisol level starts hyperactivating these structures. Previous lectures, we talked about what happens when you go into the amygdala hippocampus and you stimulate it. The person might hallucinate, might get complex hallucinations. How many here have seen charming little Disney cartoon, Snow White and the Seven Dwarfs? Okay, just about everybody. Let's consider what happens in that story. Okay, here's beautiful little Snow White, and there's the evil queen, her stepmother, of course, and who's the fairest one of all? It's the queen, uh-oh. Little Snow White's growing into a beautiful woman, now she's the fairest one, so Queen decides she's going to have Snow White killed, sends her out with the head forester, with the instructions, take her out to the forest, I want you to cut her heart out, put it in a little box, bring it back to me.
Bring back her heart.
Well, the forester takes her out to the woods, and little Snow White, she's innocent and sweet, and just a darling little girl raised in this protective environment. And she's taken out to the woods, and the forester tells her, Queen's told me to cut out your heart. And little Snow White, well, obviously she feels a lot of fear. Suddenly she's under stress. Fear. Amygdala. Amygdala, we know, you stimulate it, tremendous fear. Continue stimulated, the person might run, okay, flee. So he tells her, want to cut your heart out and put it in this little box. Run, Snow White, run.
Run! Run away! Hide! In the woods, anywhere! Never come back! Now go! 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 Run! Run! Hide!
Run, Snow White, run. And she's in a panic. She's totally terrified what's going to happen, and she starts running into the forest. And what happens? She's running in the forest, and all at once, the trees start bending down towards her, and they look like they have arms, and they look like they have eyes, and she's just totally terrified. And we can all relate to this, because if you've ever been out in the woods late at night and wandering, you can almost sometimes see things that might not be there, or hallucinate, or see scary things. So under terror, we know, under terror, people will sometimes hallucinate. That happens sometimes under incredible terror, the person might hallucinate. We can call it a sensory distortion, or we can call it hallucination in the case of Snow White. Person with the tumor seizure disorder, electrical stimulation, they will have incredibly vivid hallucinations. They'll see devils, they'll see God, they will see angels, they'll see they'll see pigs dressed as people walking around in high heels. Incredibly vivid, powerful hallucinations. And the more and more you move towards the anterior temporal lobe, where that amygdala and the anterior hippocampus, anterior main front, hallucinations get incredibly more and more and more profoundly vivid as you move anterior to the temporal lobes. Hear stories, little kids come in and say that they were being molested and terrorized by demons and devils, and people were doing satanic rituals, and of course that's not true. The child's just making it all up, right? Of course people weren't dressing in these costumes and engaging in all these horrible satanic rituals. But what if you're a little kid being terrorized and tortured and sexually assaulted, and you're incredibly frightened, and it's going on over and over, and you're so terrified you also begin to have Snow White's type of sensory distortions. Snow White, if we talked to her later, she would have told us that there were these devils and demons out there in the forest. She would have believed that. She would have remembered it. It would have gone into her memory.
But you don't know what I've been through. And all because I was afraid.
In fact, little Snow White might start having flashbacks of this happening. Why might a person have flashbacks? Amygdala, hippocampus being hyperactivated. There might be structural changes in this area. In consequence, we know in PTSD, people sometimes have flashbacks. If something horrible happens to you, sometimes people will go over it and think about it for day after day after week, and have to tell everybody about it over and over and over because they can't get it out of their mind. So we can say that this area is being so activated that the person is constantly re-experiencing it, constantly undergoing the trauma, and that's stressful too. So now they're having this bad feedback mechanism. So it's almost like a downward spiral because they're having having similar emotional reactions. So they're having flashbacks, can't stop thinking about it. Or what might happen if these structures get damaged, the person might forget. They might develop amnesia, have no memory of what happened, and it's called a repressed memory. And the people who are addicted to ignorance will tell you, oh, there is no such thing as repression. Well, there is. It's been experimentally demonstrated in animals and in humans by stimulating these areas. Yes, there is repression. What can happen, though? A person forgets, and this also happens with PTSD. A person has PTSD, they hear a loud sound, tremendous startle reaction. They might have the whole experience come to them again. Startle, fear reaction, that's the amygdala. So even if the memory is repressed, so to speak, let me give you a case of a woman, jogger in New York, who was brutally raped, beat, hit with bricks, and she was found later wandering with no clothes, and they determined that she had been brutally raped. But she had no memory. Last memory she had was of jogging. But obviously she'd been beat up, obviously she'd been raped, all the signs of that, but she had no memory of this happening whatsoever. The people addicted to ignorance will tell you, oh, well then, she's faking, there is no repressed memory, but this woman had no memory of what occurred. But what happened is after she did some recovery, she went back with a boyfriend along the trail, saw a pile of bricks, and suddenly a big part of the memory came back to her. So it's not like the memory, the memory might be gone, but it also might be, because under abnormal conditions, it could be stored in a place where you later can't find it. It's like you lose your computer hard drive and you think everything's gone, but they can go in there and still find it through other means. So sometimes the memory is still there, and in consequence, think about dreaming. Wake up in the morning, remember none of your dreams, you come to school, you're walking around, you see somebody with a little balloon, you go, oh yeah, I remember I had this dream last night. It happens all the time. Context, there are things that called recognition memory that can trigger the memory and help you recall it. That is something common in women young women being molested and having no memory of it, and they're watching a movie about being molested or seeing something on TV, and suddenly this memory comes back, and some people say, oh, the therapist put that in her mind, or, you know, that couldn't have happened. Why didn't she remember it before if this really happened? Well, it's because it happened over and over and over and over and over and over again, and if you damage, we know, if you damage these structures, you lose memory. And in fact, there have been studies looking at MRI at people with PTSD, and it found in the right hemisphere shrinkage of the amygdala and the hippocampus. Definite evidence in the right hemisphere, which we know is the more emotional half of the brain, that these structures are actually visibly smaller.
And evolutionary theory, would there be a reason for it?
Freud also said in Exploring the Unconscious that many people forget these things for a reason, so you're not terrorized or traumatized by it even further. Sometimes forgetting is very beneficial. It's better, while learning, like you go in a certain area, the tiger or the lion chases after you and you get away, you learn not to go back there. But if you put the person in a situation over and over again, once it's not, we're talking about a unique type situation, modern society, where somebody can be put in a war zone for a long period of time and repeatedly subjected to, I mean, before it's bows, arrows, spears, now it's explosions, body parts blowing all over the place. It's not part of the evolutionary experience to have this happen over and over again. So they're really, it's adaptive to learn, but it's not adapted to have a horrible experience over and over again. And in consequence, they develop abnormalities such as post-traumatic stress disorder. It was in the First World War and the Second World War, it was called shell shock. And they thought that the guys having this were cowards. You're a coward. Get back out there and fight. There was no sympathy whatsoever for these soldiers. I've got film of them even slapping these soldiers around, trying to act like a man, go back out there and kill some more people. And in fact, so it used to be called shell shock. Now we call it PTSD. If you're chronically being stressed, even after you go into a nice, warm, safe environment, it's years later, you might always feel anxiety, always anxious about something. Why is that? Go into the amygdala with animals or humans, stimulate, and what the animal will do first is anxious glancing. Human will say they feel anxiety. Stimulation continues, tremendous amount of fear. Continues even further, person runs, or they become petrified. So, if you have all this abnormal activity, I mean, if you're in a fearful environment, if you're being stressed, traumatized, this area is being hyperactivated, then it can be damaged, so you're constantly recalling, or you're not remembering at all, or you're chronically under stress, so that anything can trigger anxiety, fear. You're always walking around feeling a little afraid, a little bit of anxiety. So we've just briefly gone over what can happen under conditions of chronic stress, is that the brain becomes adapted to be under chronic stress, and then what happens is even under low levels of stress, the person can become extremely stressed. So even little things can make the person extremely stressed out if the brain has been adapted to being under stress all the time.